Basics of AC and DC voltage, detailed description. The image explains the basics of AC, alternating current, voltage and DC, direct current, voltage, the two main types of electrical voltage used in electrical and electronic systems. Voltage is the electrical force or pressure that pushes electrons through a conductor, allowing electric current to flow. It is measured in volts, V. Although both AC and DC voltage perform the same basic function of supplying electrical energy, they differ in the way their voltage changes over time. AC voltage continuously changes its magnitude and direction, while DC voltage remains nearly constant and flows in only one direction. Understanding the difference between AC and DC voltage is essential for learning electricity, electronics, electrical engineering, and power systems. The left side of the image illustrates AC voltage using a sine wave, which is the most common waveform produced by electrical generators. The vertical axis represents voltage, V, and the horizontal axis represents time, t. The waveform rises smoothly from 0 to a maximum positive value called the peak voltage, Vp, then decreases back to 0, continues to a maximum negative value, and finally returns to 0 to complete one full cycle. This repeating pattern continues continuously. The time taken to complete one full cycle is called the period, t, while the number of cycles completed in 1 second is called the frequency, f, measured in hertz. The image also shows the equation for the instantaneous AC voltage, V, T, is equal to Vp times sin, 2 pi ft plus phi, where Vp is the peak voltage, f is the frequency, T is time, and phi is the phase angle. This equation describes how the voltage changes continuously with time. The image introduces the concept of RMS, root mean square, voltage, which is the effective value of an AC voltage. Since AC voltage is constantly changing, engineers use the RMS value because it represents the equivalent DC voltage that would produce the same heating effect in a resistor. The RMS voltage is calculated using the formula Vrms is equal to Vp2, which is approximately 0.707 times Vp. Similarly, the peak voltage can be calculated using Vp is equal to 2 times Vrms, which is approximately 1.414 times Vrms. These relationships are widely used when designing electrical equipment, transformers, motors, and power systems. The image provides a practical example using a 230 V AC household outlet. The voltage printed on the outlet is the RMS voltage, not the peak voltage. Using the formula Vp is equal to 1.414 times Vrms, the peak voltage is calculated as Vp is equal to 230 times 1.414 325 volts. This means that although the electrical outlet is rated at 230 VAC, the voltage actually reaches approximately plus 325 volts at its positive peak and 325 volts at its negative peak during each cycle. This alternating voltage powers household appliances such as fans, refrigerators, washing machines, televisions, air conditioners, and electric motors. The right side of the image explains DC voltage. Unlike AC voltage, DC voltage remains constant over time, so its waveform appears as a straight horizontal line. The voltage does not change direction or polarity, providing a steady electrical supply to electronic devices. Since the voltage is constant, the average voltage is equal to the DC voltage itself. DC voltage is produced by batteries, solar panels, USB chargers, power banks, and regulated power supplies. Most modern electronic devices operate internally using DC voltage because sensitive electronic components require a stable power source. The image also presents simple formulas used in DC circuits. The current flowing through a resistor is calculated using Ohm's law. I is equal to VDC-R, where I is the current, VDC is the DC voltage, and R is the resistance. Electrical power is calculated using P is equal to VDC times I, where P is the power measured in watts, W. These equations help engineers calculate the electrical power consumed by devices and determine the correct battery size, wire thickness, and circuit protection. A practical example shown in the image is a smartphone charger. A smartphone typically operates using 5 volts DC. If the phone draws 2 amperes of current while charging, the electrical power consumed is calculated using P is equal to V times I is equal to 5 times 2 equals 10 watts. This means the charger supplies 10 watts of DC power to charge the phone battery safely and efficiently. Similarly, laptops, tablets, LED lights, routers, and many electronic devices use regulated DC voltage for reliable operation. Another everyday example can be seen in a home electrical system. Electricity generated at a power station is transmitted as AC voltage because it can be easily stepped up to very high voltages for efficient long-distance transmission and then stepped down again for safe household use. When this AC electricity enters devices such as televisions, computers, mobile phone chargers, or LED lamps, an internal power supply converts the AC voltage into DC voltage before powering the electronic circuits. This conversion allows digital components such as processors, memory chips, sensors, and displays to operate correctly. A simple way to understand the difference between AC and DC voltage is by comparing them to the movement of water. AC voltage is like ocean waves moving back and forth repeatedly, constantly changing direction. DC voltage is like water flowing steadily through a pipe in one direction without reversing. Both forms of voltage carry energy, but they are used for different purposes. AC is ideal for generating and distributing electrical power over long distances, while DC is ideal for powering electronic devices and storing energy in batteries. In summary, the image explains that AC voltage continuously changes its magnitude and direction, forming a sinusoidal waveform characterized by peak voltage, Vp, RMS voltage, Vrms, frequency, F, and period, T. AC voltage is commonly used for household electricity and industrial power systems because it is efficient for transmission over long distances. DC voltage, on the other hand, remains constant over time and provides a stable source of electrical energy for electronic equipment such as mobile phones, computers, LED lighting, solar power systems, and battery-operated devices. Understanding the characteristics, formulas, and practical applications of both AC and DC voltage is fundamental for learning electrical engineering, electronics, renewable energy systems, and modern electrical technology.